Welcome you all in my first lecture. So, I will talk about n-dimensional Euclidean space first, the definition, then I will talk about little bit of its properties, then I will introduce the notion of distances in Rn, and then of course I will introduce the notion of open set, closed sets, compact sets, connected sets, convex sets. Those are the notions you are familiar with in context of real line. But similar sort of context you will see that can be introduced in the context of n-dimensional Euclidean space. Then I will introduce the notion of sequences in Rn and its convergence. Since I have the concept of distance, you will see I can introduce the notion of convergence in Rn. Like similar way you know the notion of sequences in R and its convergence. Then I will introduce the notion of Cauchy sequences, and then later I will introduce the notion of functions, that means functions of several variables, that means functions from n-dimensional Euclidean space to m-dimensional Euclidean space. And then I will talk about the concepts of limit and continuity of functions of several variables. Let us see what is the definitions of Rn first. Okay. So, the space Rn is the collection of n tuples, that means it is a collection of tuples where the components like x1, x2, xn they are coming from R, and it is the collection of all tuples x. I will denote the point in Rn in capital letter X, where the component small x1, small x2, small xn's they are coming from the real line. First thing is that we can say that Rn is a metric space. Now you can ask, what do I mean by metric space? So metric space means, so let me just talk about little bit about the definitions of metric space. So let X be a non-empty set. Define a metric or distance from x cross x to positive real line, that means closed interval 0 to open infinity, is a function which satisfies the following three properties. What are the properties? First is the non-negativity, second one is the symmetry, and third one was the triangle inequality. What is non-negativity? That means distance between any 2 points xy is positive and d of xy is 0 if and only if x is equal to y. That is the first one. Second one is the symmetry, that means distance between x and y is exactly equal to distance between y and x, and that should true for all xy. And third one is the triangle inequality, that means distance between x and y which is lesser equal to distance between x and z plus distance between z and y, and if it is true for, it should true for all x, y, z in X. So if I have a set X along with this metric, then I will say that X comma D is a metric space. In particular, if I consider X is equal to Rn, and if I give the notion of distance between 2 points in the n-dimensional Euclidean space, like take A as small a1, a2, an and B is equal to small b1, b2, bn, 2 points in Rn. Now I am defining the distance which is nothing but the norm of A minus B, which I am saying that it should be like normal Euclidean distance. What does it mean? That means what you do, you take the coordinate wise difference, that means a1 minus b1, a2 minus b2, an minus bn, take the square it, sum it up and take the square root. So that means it is nothing but the square root of a1 minus b1 square plus a2 minus b2 square dot dot up to an minus bn square. This is the called Euclidean distance in Rn. So once I have the set x is equal to Rn, and if I give the notion of this distance like that, then one can check that Rn with this distance it becomes a metric space. Now Rn is also a vector space, that means if I have an n-dimensional Euclidean space Rn, if I take two vectors or 2 points A and B from Rn, and if I give the operation like vector addition, like A vector plus B vector, which is nothing but the component wise addition, that means if a1, a2, an, small a1, small a2, small an are the components of capital A vector, and small b1, small b2, small bn are the component of capital V vectors, if I give the notion of A plus B is nothing but a1 plus b1, comma a2 plus b2, comma n plus dot dot dot, comma n plus bn. This is the called vector addition, that means component wide addition. And if I have a lambda, if I take scalar from the real field R, and I give the meaning of scalar multiplication as lambda times a vector is nothing but it just component wise multiplication, that means lambda times a1, lambda times a2, lambda times a n. Okay. So, once I have the notion of additions and scalar multiplications, then Rn is a vector space with the above mentioned vector additions and scalar multiplications. Rn is also a nonlinear space. Now, what is the meaning of nonlinear space? If I have a vector space V over a real or complex field, our norm is a map from the vector space V to the positive real line, that means closed interval 0 to open infinity, which is a function satisfying the following three properties. What are the properties? First is the non-negativity, second is the homogeneity, and third is the triangle inequality. So, what is non-negativity? That means norm of the vector is always positive for all V, norm of V is equal to 0 if and only V is equal to 0. Homogeneity, that means if I take the norm of scalar multiple times the vector, then mod lambda will come out and we will have the norm of V, and this should be true for all V in V and all scalar lambda. And third one is the, which is very important, that is known as triangle inequality. That means if I take the norm of sum of two vectors u plus v, it should be dominated by norm of u plus norm of v, and it is true for all uv. So, that means if I have a vector space over some real or complex field, and if I define a norm which satisfies these three properties, then the vector space with respect to this norm, it becomes a nonlinear space. In particular, if I take V is equal to the n-dimensional Euclidean space, now I want to introduce the notion of norm corresponding to a vector in Rn, like if I take a point V which is V1, V2, Vn in Rn, and I want to define the notion of norm of V is nothing but the length of the vector V. What is the length of the vector? Is nothing but the square root of V1 square plus V2 square up to Vn square. So, that means take a vector V, small v, from V and give the notion of norm V, which is nothing but the length or magnitude of V, which is nothing but this. So, given a vector, I am giving the notion of norm. Then one can easily check that this norm with respect to that norm Rn becomes a nonlinear space. Now, one can also say Rn is an inner product space. Now, what is the definition of inner product? Again, if I start with a vector space V over a real or complex field, and inner product I denote it as this symbol, which is a map from V cross V to R or C, that means the corresponding field I am considering of the vector space, which satisfies the following four properties. What are the properties? First property is the linearity. That means inner product between U plus V and W, it should be exactly equal to inner product of UW plus inner product of VW, and this is true for all UVW in V. That is the first, and all scalar. Okay, I think this is a mistake. There is no point scalar is there. So, just the first is that for all UVW it should be true for capital V. Second one is the homogeneity. So, what does it mean? That means if I take lambda times inner product between lambda u and v, then lambda will come out. What is remaining is the inner product between u and v, and that should true for all uv and all scalar lambda. Third one is the symmetry. That means inner product between u and v, it should be exactly equal to the complex conjugate of the inner product of v and u. Okay, here bar actually this denotes the complex conjugate. And third one is the positivity. What is positivity? If I take any non-zero vector u, then inner product between u and u, it should be strictly positive. So, therefore, if I have a vector space over some field R or C, and if I have an inner product which satisfies these three properties, then I will say that my V with this inner product it becomes a inner product space. In particular, if I take V is equal to n-dimensional Euclidean space, now if I define the inner product between two vectors, so that means I am considering u and v two vectors in Rn, and I am defining the inner product which is nothing but the dot product. That means you have a component small u1, small u2, small un of u and v1, v2, vn of v. What we have to do? You just product. First component product, that means u1, v1 plus u2, v2 plus dot 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 up to un, vn. If I define the inner product like dot product as like that, inner product between u and v is nothing but the dot product, that means u1, v1 plus u2, v2 plus dot 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 un, vn, then one can check that Rn with respect to that inner product, it becomes an inner product space. So, here are some couple of results. So, what it says that if I have a nonlinear space, it always a metric space. What does it mean? That means if I have a nonlinear space, I can have the concept of distance which is induced from the norm. That means starting with a nonlinear space, define the metric distance between u and v. Take any 2 points u and v, give the meaning of distance which is nothing but norm of u minus v, because I am starting with a nonlinear space. Then one can check that nonlinear space with respect to that matrix, it becomes a metric space. but the converse is not true. What does it mean? That means I have an example of a metric space x comma d where the metric cannot be induced from any norm on that space. That is all. So there exists a metric space. See, there exists a metric space whose metric is not induced by norm. So that means metric space cannot imply it's a non-linear space. So that means if I can have an example of a metric space and that metric cannot be induced by any norm on X like this way. So for example, if I have a R and if I give in this metric D, then one can check that it is a metric space, but that metric D cannot be induced by any norm on R. Similarly, if I have an inner product space, then it is always a nonlinear space. What does it mean? That means if I have an inner product space, I can give the definition of one norm induced from that inner product. That means, so given inner product space, define norm of V, which is nothing but take the inner product between V and V, which is non-zero. That means I can take the square root of it. One can check that with respect to that norm, your inner product space becomes a nonlinear space. However, the converse is not true. That means I have an example of a nonlinear space where that norm cannot be induced from any inner product on that space. So therefore, that's what I have written. There exists a nonlinear space whose norm is not induced by any inner product. So therefore, nonlinear space will not imply it is an inner product space. Some example. What is the example? You start with an two-dimensional Euclidean space. You define this norm. One can check that it is a nonlinear space. However, that norm of x comma y, which I denoted as maximum of mod x comma mod y, that norm cannot be induced by any inner product on R2. So therefore, nonlinear space will not imply it is always an inner product space. Okay, so now I already introduced the notion of n-dimensional Euclidean space, which is nothing but the collection of n tuples where the components small xi are coming from real line R. Okay. Now, if I take 2 points which I denote it as capital X and capital Y, then I know the distance between x and y, which is nothing but norm of x minus y, and which is nothing but the Euclidean distance. That means it is nothing but the square root of x1 minus y1 square plus x2 minus y2 square dot 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 up to xn minus yn square. Okay. So once I have the notion of distance in n-dimensional Euclidean space, then I can talk about the concept or notions of open ball. What is the definition of open ball? An open ball with centered capital A, which is nothing but small a1 to an, and radius r, which I denote it as ball of centered A and radius r, and it is defined by, it is the collection of all those point x in Rn such that distance between x and A, which is strictly less than r. Okay. So that means if I draw a picture, at least in the case of R2, what is going on, if I have a point A, then I can draw a circle centered A with radius R. So all those points. So this is my point A and this is my radius R. So all those points in those balls. So this is actually the definition of open ball. It is also denoted by B suffix R at the point A, that means ball of center A radius R. It is also called an open neighborhood of A. Sometimes it is denoted by neighborhood, N stands for neighborhood. So A comma R, N of A, or N suffix R of A. Now once I have the notions of open ball or open neighborhood, then I can talk about the concept of interior point and limit point in the set Rn. Okay, so what I am doing, let S be a subset of Rn. A point x naught is said to be an interior point of S. So I have a set S. So this is my, suppose, let me just draw in R2. So suppose this is my S. Okay, this is my set S. Take a point x naught. Okay, I am saying that it is an interior point of the set S if there is an open neighborhood in x naught which is fully contained in that set. That means what I am doing is that, so if there is, suppose this is an open ball, okay, with centered x naught, this is my x naught, and which is fully contained in that set. So therefore those kind of point I will say that it is an interior point. The set of all interior point of S is called the interior of S, which I denote it as S naught or int of S. Okay. And what is the definition of limit point? Limit point is that take a set S. Suppose this is my, once again, this is my set S. Take a point x naught, suppose lies here. Then it says that a point x naught is a limit point or accumulation point or cluster point if every neighborhood, this is very important, every neighborhood n x naught of x naught which contains at least one point from the set S except the point x naught. So that means suppose this is my point x naught, suppose here whatever neighborhood I can take, open ball or open neighborhood, always there exists a point in S which is different from this point. So therefore this sort of point I call that it is a limit point. The set of all limit points of S is called the derived set of S, and I denote it by S prime or DER of S, set of all limit points of S. Now once I have the notion of limit points or interior point, then I can talk about the concept of open sets in the n-dimensional Euclidean space. Okay, so let's start with a set S subset of Rn. A set S is called open in Rn if each point of S is an interior point of S. So that means, so if I have a set S subset of Rn, if I take any point inside S, it should be an interior point. The set S is called open if each point inside S is an interior point. That means, what is the definition of interior point? I know that take a point inside that, there should exist an open ball which is fully contained in that set. For example, again, let's draw some set in R2 and take an ball of center 0 and radius say 1. This is an open set. Why? Because, so I am bad in drawing, okay. So if I take any point here, okay, so I am to show that this is an interior point, and it is indeed the case. Why? Because I can have always a small open ball which is fully contained in that set. So therefore each point is an interior point, and therefore the ball, I can say that ball of center 0 radius 1, it is an open set. So that is, I have written, that is for each point x in S there exists an open neighborhood or open ball around the point x which should fully contain in that set. So that kind of set I will say that it is an open set. What is the definition of closed set? A set is called closed in Rn if its complement is an open set in Rn. So that's the definition. Now this is one of the characterization. A set S is closed if and only if it contains all of its limits points. So a set, I will say that, of course, one of the definitions of closed set is that its complement is open. Another way I can say that a set is closed if and only if it contains all its limit points. Now I can talk about the notion of bounded sets and compact sets. So a similar sort of notion you are familiar with in the context of real line. So what is that concept of bounded set? Again, you start with a set S subset of Rn. I will say that a non-empty set S is bounded set if there exists an open ball with some center x naught and some finite radius r naught such that my S fully contained in that ball. So again, you draw a picture in R2. Suppose this is my R2, take a set, suppose this is my S, and I will say that this is a bounded set. Why? Because I can draw a big open ball with some center x naught and say finite radius r. So if that things happen, then I will say that my set is always bounded. That means given a set S, I have to find an open ball if there exists an open ball with some center x naught and radius r naught, and if that open ball fully contains my set S, then I will say that my set S is bounded. Now next come to the concept of compact sets. I know in real line what is the definition of compact sets. We know that a set is compact if it is closed and bounded. A similar sort of fact is also true in context of n-dimensional Euclidean space. A definition: a non-empty set S of the Euclidean space Rn is said to be compact if it is closed and bounded. Another two notions, which is connected set and convex set. So start with a set S which is subset of Rn. I will say that an open set S is said to be connected in the Euclidean space Rn if any two points of S can be joined by a path which sometimes a continuous curve such that the path gamma lies entirely inside that set. Okay, so that means again draw a picture in R2. So suppose this is my R2, suppose you have a set S again. So if I take 2 points, okay, what I am saying is that any 2 points, suppose if I take any 2 points that can be joined by a path, and that path should lies entirely in that set. Like I can draw a path here, and that path, so joining this point and this point, okay, and that path is fully contained in that set. If these things happen, I will say that that set S is connected. For example, example of a set which is not connected, again you draw. Suppose this is in R2. What I am doing, take open ball, take another open ball. Suppose this is S1, suppose this is S2. Now you define a set S which is nothing but S1 union S2. Okay, I will say that that set S is not connected in R2. Why? Because take a point from S1 here, take a point from S2 here. Now you just join a path between these 2 points. So suppose I am joining here. Now this path is not fully contained in that set S. Why? Because this is the portion which lies outside the set. So therefore this set is disconnected, it is not connected. I have already written a set is said to be disconnected if it is not connected. Next definition is the definition of convex set. So a set S is said to be convex if every straight line segment L joining any 2 point S which lies entirely inside that set. Okay, and that kind of set is called convex set. That means if I have a set S, take 2 points, join it by just a straight line segment. That is very important. You just take 2 points, join it by line segment, and that line segment has to be in that set. If this is true for that set, for any 2 points, line segment joining these 2 points lies entirely in that set, I will say that that set is convex. So first observation is that every convex set is connected, but the converse is not true. That means all connected set need not be convex. For example, again come to R2, consider this set. Okay, my claim is that this set is connected, this is connected, but not convex. Why? Because if I take 2 points here, now what is the definition of connected set? So that means I should join by a path which is entirely lies in. So this is the path I can say, and this is fully lies in that set, not an issue. So therefore this is connected. But what is the definition of convex set? So the line segment, that means if I draw a line here, in this point, this 2 point, this point and that point, so this line segment, so this portion is lies outside the set. So therefore this set is a connected set, but it is not convex set. Now example of some convex set, again you can give it, come back to R2, okay, take an open ball, okay, open ball with center 0, radius 1, this is a convex set, because if I take any 2 points, line segment always in that set. So this is a convex set. So all convex sets, so if I take any 2 points, I can join by a line. In fact, this is a path and that is fully contained. So therefore this is a convex set and it implies it is a connected set, but the converse is not true. Here is the example. Okay. So now I have introduced the notion of distance in the Euclidean space. Then I talked about the concept of limit point, interior point. Then I talked about the concept of open set, closed sets. Then I talked about the concept of compact sets, connected set, convex sets. I need those kind of concepts later on when I will talk about functions from n-dimensional Euclidean space to m-dimensional Euclidean space, the concept of limit continuity. Then if I take a set which is say compact in Rn or say connected in Rn, how the interplay between compact sets and connected set with that continuous functions, how it interplay, what is going on, that is why I need those kind of concepts. Of course, I introduced the concepts of distance, and that will come while talking about the convergence of sequences. So now I should start with the concept of sequences in Rn. Before that, let me just recall what is the definition of sequence in R. Okay, what is the definition of sequence in R? So a sequence xk, I will denote like that, xk in R. What is that? It is a function. It is a function from set of all natural numbers to set of all real numbers. So since it is a function, so that means the value of x at any natural number, it is nothing but x suffix k, which is the point in that sequence. So that means a sequence in R is a function from set of natural numbers to R. So that I say that real sequence, which I denoted by xk. Or I can say that what are the elements like x1, x2, x3, so on and so forth. Okay. So what is the example? Some examples of sequences. For example, this is one sequence, xk, which is 1 by k. So what is the function here? So function here is that if I take x is a function from n to r, so each natural number k goes to 1 by k. This is the function. So this is a sequence. Another sequence, so I have first point is x1 is equal to 1, second point x2 is equal to 2. Now this is the recurrence relation, xn is equal to xn minus 1 plus 3xn minus 2 for n greater or equal to 3. So then what is my x3? So I have a x3 which is nothing but x2 plus 3x1. Now I have the value of x1, I have the value of x2, so you can have the value of x3. Similarly, once I have the value of x2 and x3, then you have the value of x4. So this is the recurrence relation. So that means you have all the points, say x1, x2, x3, and so on. So this is a sequence. Another example of sequence, so whose first element is 0.1, second element is 0.11, third element is 0.111. So that means the natural number 1 goes to this 0.1, 2 goes to 0.11, 3 goes to 0.111. So therefore this is a function, and therefore each element of the sequence I can write, and therefore this is a sequence. Now, so similar sort of definitions I can take in the context of n-dimensional Euclidean space. What is the difference? So difference is nothing. Again, it is a function from the set of natural numbers, but it should take the values in n-dimensional Euclidean space instead of R. Earlier it was a real sequence, so that means it is taking the value in R, but now I am talking about the sequences in Rn, that means it should be a function from set of all natural numbers to values in Rn. So that's what I have written. A sequence which I denote it as xk in Rn is a function from set of natural numbers to n-dimensional Euclidean space, because I am talking about the sequence in Rn given by x, the value of x at any natural number k, which is nothing but x suffix k. Now in that case, what is x suffix k? X suffix k is a point in Rn, so that means it is of the form, so that means xk should be an n-tuple in Rn. So therefore I have written explicitly, like x1 should be a point in Rn, that means it is nothing but x11, x12, x1n, x2 is nothing but x21, x22, x2n. In particular, if I write xk, what is this? This is nothing but small xk1, small xk2 up to small xkn. So this is the definitions of sequence in Rn. As I said, each xk is an n-tuple or element in point in Rn. Now what is more important, you should realize that when I am talking about the concept of sequence xk in Rn, it induces corresponding component sequence in R. What does it mean? That means if I have a sequence xk which is like say xk1, xk2 up to xkn in Rn, then this sequence in Rn is induces n component sequence in R. So that is capital Xk, this is small, so that means I can have the sequence say small xk1 up to small xkn. So this is a sequence in R, this is also a sequence in R. So that means given a sequence capital Xk in the n-dimensional Euclidean space, I will have n component sequence in real line. Later on you will see many things. If I conclude on the sequence capital Xk in Rn, it will have the similar sort of properties in, or I can say many things about the component sequence in R, because I know many results in the sequences in R. So therefore I have n many component sequence. Now using that conclusions on those component sequence in R, can I talk about some conclusions about the sequence capital Xk in Rn and vice versa? Later slide you will see those kind of connections are there. Before that, let's see some example. For example, if I have in R5, for example, xk, that means it should have 5 components, right? So this is 1, 2, 3, 4, 5. So first component sequence is nothing but 1 by k. Second component sequence, it is k minus 1 square. Third component sequence, it is a constant sequence, 0 sequence. And fourth component sequence is k square plus 5k. And fifth component sequence is 1. Okay. So that means, so if I have a xk, this is a sequence in R5, that means 5-dimensional Euclidean space. It corresponding to that sequence xk in R5, I have 5 component sequence in the real line. Now in R3, again it should be a point in the 3-dimensional Euclidean space. So therefore I have x1 is equal to 1, 1, 1, x2 is equal to 2, 2, 2, and then I have the recurrence relation. So therefore if I know x1, x2, you can have the, by computation you can have x3. So x3 means what? 5 times x2 plus 3 times xn minus. So that means I can have x3. What is my x3? It should be 5x2 plus 3x1. But I know the value of x1, I know the value of x2, so I know the value of x3. Similarly, if I know value of x3 and x2, I can know the value of x4, and so on and so forth. So by this recurrent relation, you have the sequence capital Xk in R3. Similarly, if I am in R2, so this is the component sequence. So x1 is a 0.2, 0.1. What is my x2? 0.22, 0.1. Now this is very nice. So what is going on? In capital X1, I have the point 0.2, 0.1. And what is x2? 0.22, 0.1. That means second component I am keeping fixed. That means the second component sequence, it's a constant sequence, and the first one is varying 0.2, 0.22, 0.222 and so on and so forth, and therefore it gives a sequence in R2. Okay, so I think I should stop here. So I just introduced the notion of sequences in Rn just like the notion of sequences in R. So this is a function in R, it's a functions from set of natural numbers to set of real numbers, but in Rn it is again a functions from set of natural numbers, but this time I am taking values in Rn. That is one of the point. Another point is that if I take a sequence in n-dimensional Euclidean space, then corresponding I have n component sequence in real line, and later you will see those component sequence, the conclusion, if I made some conclusion on the component sequence, then I can talk about the conclusion of the big sequence capital Xk in that Euclidean space. If I have the conclusion on the sequence capital Xk on the full n-dimensional Euclidean space, then I can conclude some conclusion about the component sequence in R. So that will come later when I will talk about the notion of convergence of a sequence in Rn. Let's stop it here. I think next lecture I will start with the convergence of sequences in Rn. Thank you.